Thank you so much for joining us. And I just want to ask first question. You're doing some really groundbreaking work at MIT and are making so many dreams of ours come true with X-ray vision. Can you tell us more about your current work and research?
Sure. First, hi Aggie. Very nice to be talking to you and I know the rest of the people on your team. Basically, I work in the high level area. You can think of it as digital health. So it's a combination of machine learning, wireless systems, and cloud and IoT. So it's something that sits at the intersection of these three. My particular work is focused on using wireless signals to sense people and to sense also to sense people and their action and movements, as well as sense their physiological signals, such as their breathing, their heartbeat, their sleep. And because we are using wireless signals, we don't put any sensors on the body. We can actually do all that sensing through walls. So even if I'm sitting in this room and there is a wall between me and the person that I want to sense, I can see their movement through the wall. I can get their respiration through the wall. I can even get their heartbeats through a wall. That's why we say, like when we talk about these systems, we say that it's moving from the wearables to the invisibles, making the environment health smart and allow the environment to use a wireless signal to sense people and their physiological signals through walls and obstacles.
That sounds really exciting. Do you have any favorite analogy to help explain this to non-experts so we can understand your work?
Yeah, so it's not an analogy, but I think maybe like the easiest way to try to understand for the layperson is like you all have Wi-Fi box at home. I mean, so imagine if that Wi-Fi box is actually much smarter than it is today. It is actually gonna sit in the background, the same shape and looks, however, has smarter brain using machine learning, and it's going to analyze the radio signals in the environment, and it's going to process them with custom neural network. And from that, it's going to actually be able to get your breathing, your heartbeat. When you walk, it will know from the wireless signal, even through the wall, just by analyzing these wireless signals that you are walking, where exactly you are, at what speed you are moving. And all of that stuff is just making that wireless box smarter by giving it a new brain that comes from neural networks.
That's so exciting. And speaking of heartbeats and other vitals, when it comes to medical data, what are some of the biggest outstanding challenges in processing this data, and how is machine learning playing into that?
Sure. So there are two ways to think about that. So the first one is why machine learning, and in fact, and we can, one of the very nice things about wireless signal is that we can sense the environment and the people without touching them. So it allows you to reach out to people and get information from them without physically touching them or asking them to do something. And even as you said, through walls. So this is a nice feature about wireless signals. However, wireless signals not only reflect off people, and the reason why you can do it actually is very much similar to vision to some extent. So the reason why you see something, you see some object, is because light reflects off this object and comes back to your eyes. So the same thing happens with wireless signal, except that wireless signal traverse walls. So you can actually start getting, you cannot see the details, you cannot see their hair and their like fingers and stuff like this, but you can see like the skeleton, let's say, of the human behind the wall using wireless signal. But for the same, using the same principle, like the wireless signal traverses the wall, and very small, minute amount of that wireless signal reflects off the persons behind the wall and comes back to your radio. And now your radio has to be extremely smart in analyzing those reflections to regenerate the object that generated those reflections. Now you asked about the challenges. The challenges are on two fronts. So the first thing is that radio signals not only reflect off people, reflects off everything in the environment. So it's actually, when it goes through the wall, some of the signal reflects off the wall, some of the signal goes inside the other room, reflects off the ceiling, the wall, the computer, everything, and the person. And not only this, it bounces multiple times. So it might reflect off me and then goes reflect off the wall. And so it creates a mess. Like imagine if somebody took the image that you see in a camera and then like created like just took all of these lights and mixed them all together. So this is how the wireless signal that comes back looks like. So it's kind of like a mess of all of these reflections, as opposed to the light signal, which has very small wavelengths and does not get mixed as much. So now the challenge is to take, like, separate or disentangle that mess from each other. So, and when you do that, traditionally, like, people try to use signal processing, but it's difficult. So they can do it only for objects, like in environment where things are, mostly the environment is empty except for a few objects. So if you think about radar kind of like that, radar using wireless signal, it reflects off an object and then you can track the object. But then the sky is mostly empty. You are not gonna get that mess that we talked about. So one of the challenge is disentangling that mess. And it turns out that actually machine learning is very good at that, because machine learning can learn from data. Like if you try to like learn very, very complex manifold, with machine learning, you are much more able to do that than with signal processing, because there is no way to describe it in a closed form or even a numerical representation of that manifold. So that's one of the challenge, and actually neural network helps in addressing that challenge. But neural network come with its own set of challenges, because actually now you are applying it to a new data modality that is very different from images or audio signal or text. So just to give you an idea, so typically when you want to train a neural network on images, you get people to label those images. So like they just give them to like many people, like crowdsourcing, and then they say, okay, this cat, dog, horse, something like that. Now, if I give you a wireless signal and say, okay, so tell me where the person is, or whether even there is a person in this wireless signal or not, you have no clue. So just a simple thing that is labeling, which you know how to do it, anyone, almost any person knows how to label images and text and audio signal. That thing becomes a challenge. You have to figure out new ways to try to label wireless signals. And of course, there are other things that are more related to the physics and the differences between radio electromagnetic waves versus visible light.
Oh, it's so interesting, and I'm also curious to learn more. But I was wondering, in terms of this technology, what really excites you most about the usage and implications of your work going forward?
Yeah. So I think there are two aspects that excite me a lot. The first aspect is really that we are doing something that before we do it, we have no idea whether it is even possible. So the first time we started doing this, like the first time we were like, okay, can we see with wireless signals through walls? We had no clue. I mean, we know at a high level that wireless signal traverse walls, but I mean, actually, what are we gonna see? Are we gonna see a blob? Are we gonna be able to tell a skeleton? Are we not gonna be able to tell people from each other? We didn't know the answer. And it was really interesting to move. I mean, of course, the first time we did it, we were like, we had the blob. We were only like able to kind of like detect, is there a person? Is there no person? And then we started being able to track the person, and then start to have a skeleton of that person, and be able, like when he sits, you see the skeleton sitting. When he waves with his hand, you see the skeleton waving with his hand. So one aspect that is very satisfying is to actually do something when you are curious about how the answer is going to look like, and whether that is possible at all, and to try to think how to make it possible. So things in our research keep surprising me. So that's I think is very interesting for any scientist, actually, is to be able to be curious and have the science come back to satisfy your curiosity. So that's very interesting. The other aspect that is interesting is actually working in the area of health and healthcare is very interesting because it touches every one of us. Like, we all are humans, we all get sick, we all know what it means to be sick, we all care about or have relatives and people that we care about that have different diseases. So it's just interesting to be able to understand that and to be able to contribute to that. And I personally believe that we need to change healthcare in general. Like, if you think about computer systems and computer science and how computer science has changed so many domains. Like, if you think about media, for example, in the old days it was TV, for example, and then now you almost watch everything online, and hardly, like, many people don't even turn on TV or don't even need to have TV. Social interaction, we used to have social interaction but in person. Now, like, social networks, like, it's just like here. I mean, it's not like you don't even think about it twice. During the pandemic, we even managed somehow to move work to the home, and the whole work structure and how people work has changed and became remote and became through these, like, the Zoom call that we are having now. So computer science has changed so much in other domain, and healthcare actually is very much ready and need disruption. And I think computer science in general and machine learning in particular can help drastically change that. Just to give you one aspect that in healthcare. So I work with patients who have Parkinson's, and I mean, Parkinson is a neurological disease. I mean, you probably have seen people who have Parkinson. They have, like, motion problems, and so you would think that if a person has Parkinson, naturally they're going to be seen at least at some point by a Parkinson's doctor. So actually, large percentage, at some point there was a study that 40% of Parkinson's patients don't get seen by a specialist, Parkinson's specialist at all. And the problem is that most of, like, when you think about diseases, most of the medical centers are, like, in certain areas, mostly typically urban, but it's just that there are few places where there are medical centers that are good and they have particular specialties. And why patients are everywhere. They are not necessarily close to those medical centers. So for a patient to go there, they have to travel for hours at least to go there. And even if they do it once, they are going to do it occasionally. They're not going to be, like, going there like the person who lives in that area. So if you have the ability to monitor all of these physiological signals in the home, and you can create that connection, like, then I don't really need to be, like, next to a Parkinson center. If I'm a Parkinson patient, all of that information can be provided to the specialist and can be even analyzed and provided at a high level and provide the semantics to the specialist. And then like anyone, like, regardless of where they live, and they can have access to specialized care. And that is a very interesting and helpful concept, and can significantly improve access to healthcare, equality between people. And we are talking about the US, so you can imagine how much the situation is worse once you go even more international.
That's such an interesting statistic there. I had no idea that 40% of patients were not getting specialists. I know recently you published a paper regarding medical self-administration, and with remote care taking off during the pandemic, and interest in digital health really spiking during this period. Can you maybe describe, particularly at a high level, how this technology and models function together?
Yeah, yeah, you're referring to our recent publication in Nature Medicine, and in that we looked at detecting medication self-administration, errors in medication self-administration. So basically, there are many medication errors. Now that this is a big topic on its own, and medication errors happen even more if you have a device for the medication, like an inhaler, like we all know, like for I'm sure you've seen like people who have asthma, they have inhalers or have COPD. And then also like I'm sure you know insulin, like you have an insulin pen, and if you are taking insulin. So when you have these kind of devices, even the errors increase because there is a particular technique for using the device. So you can ask two types of questions. You can ask questions that are related to medication errors that are related to the first level that we all understand. Okay, did the patient take their medication? Did they take it on time? Are they taking it regularly? So that's one level. But then you can ask even more detailed information. Are they doing the technique of the taking the medication? Is that done correctly? Like for example, if I have inhaler, it's not enough just I take a puff. It's like I have in principle you have to shake the inhaler and then take the inhale the dose, and actually you should hold the dose. I think I don't remember, but maybe like 10 seconds. Like there is a particular period that you need to hold the dose, and then you can exhale. If you don't do this, it means that you didn't get the full dose, and as a result, you didn't get the full effect of the medication, and you didn't get the outcome that is desired. Same way, if you are using an insulin pen, for example, you have to prime the pen, you have to hold it for 10 seconds. So you can ask these like more detailed questions, not just whether the patient has taken their medications or not. You can ask this question, but you can ask more. You can ask, does the patient take the medication in the appropriate way? Did they follow the guidelines? Did they like wait before exhaling after taking a dose from the inhaler? Did they prime the insulin pen? So to do this, what we did, we use these wireless signals, and we analyzed the wireless. We put our device, analyze the wireless signal as people are using these inhalers, these insulin pens. And what we show is that not only we can detect whether patients are taking their medications or not, we can actually detect when they miss certain like important step in taking the medications. Like for example, if I took like a dose from my inhaler and I didn't, for example, hold that dose, I did not like wait until exhaling for the appropriate amount of time. So you can think about taking medications, particularly when you are working with medications that have like device-based medications like inhalers, insulin pens. It's an action, it's a composite action that has multiple steps. So what you want a machine learning model that not only detect whether an event has happened, but actually it detects the composite event, and it detects whether there are certain missing, like I probably took my the dose from my insulin pen, but I forgot to prime the pen, for example. So whether I took it appropriately, and also whether I followed the guideline. So that was the work that we did. And of course, being able to do this with a device like a wireless box is like people are not going to have cameras in their homes. That's like very difficult to convince people to just like put cameras. Also, you have to put cameras in so many places because the person is like, if the camera field of view is narrow. So with this, you can have an understanding of how the patients are taking their medications and whether they are taking it on time, and also whether they're taking it appropriately. And you can convey that information to the medical professionals.
That's such an interesting point with the camera and the wireless signals. Those problems, something to think about for sure. And I was just also wondering, in terms of challenges, in your opinion, what would you think needs to be addressed in the next 2 to 5 plus years?
Yeah, so I'm going to talk about challenges in maybe application of like, or what we call health ML. Like, okay, so the intersection between machine learning and healthcare. When you are working with medical applications or health data, I mean, you have the standard problems that happens whenever you are talking about a machine learning or a deep learning model, but certain problems become even harder. So just to talk about a few things. So one of the things is, of course, medical data is not very accessible, and we don't have millions of medical like MRI images for training our models, and so in contrast to many other data where we run very successful machine learning models, like on videos, images, and audio or text, in the medical domain, the data is scarce, or at least the access to the data, like the data that you can access as a researcher typically is not as huge. So you need to work with limited data. This is one thing. The other thing is there is a huge imbalance in the data. So, so for example, let's say that you want to design a machine learning model to detect whether somebody has some disease. I mean, let's just, since we talked about Parkinson, let's say that whether someone has Parkinson. Actually, that would be amazing because Parkinson, people tend to have Parkinson for 5-10 years before they are diagnosed. So if you can do that with machine learning, that would be great. But the thing that you have to remember is that the vast majority of the population doesn't have Parkinson's. So even if you get an accuracy that is very high, that is still going to mark many people who don't have Parkinson as having Parkinson's, even if your accuracy is 90%. Okay, so still, because the percentage of people who have Parkinson is only 2% of the population, you're still going to label so many people as having Parkinson when they don't. So as opposed to your typical application, various diseases can be like very rare, and the models, the accuracy that you need from your model is going to be much higher to be able to solve a real problem and not to label people incorrectly. So this is another thing. So basically, how do you design systems that achieve this very, like we typically are very happy if we can get 90% accuracy, but in many cases here it's not enough. So that's one thing. The other thing is that really these systems are not, so one of the things that actually annoys me sometimes in machine learning researchers is, and it's so unfortunate, and some of our students even like have this attitude, is that they want the data to come to them and they think of it like a problem set. It's like, okay, you give me the data and everything, I'm gonna think about the model and I'm gonna solve it. But in healthcare, it doesn't work like this. And actually in many domains where like, other than like domains like vision, where there are very like curated data sets for specific problems and so on. So you really need to look at the problem holistically. You need to think about how do you acquire your data, how do you clean your data, how if there is not enough data, is there other things, other data so you really need to think holistically about the problem, both in terms of how you solve the problem, and also you need to think about the application of this problem. Is this really important? Sometimes you can have very nice machine learning technique that can discover interesting information, but it will be impossible to use it in practice, just because this is not how people behave, or this is not how physicians interact with patients. Or so you have to take a much more holistic approach to the problem. You have to be motivated by the problem as opposed to by the solution.
And a little bit separate from what we were just speaking about, I was wondering if you could discuss your trajectory and how you got to machine learning, computer vision, and utilizing wireless networks.
I see. So I have very unusual path. So so I come from Syria originally, and actually like when I first was thinking about career, I first started by going to medical school. And in Syria, you don't have pre-med, so you go to medical school. So I went to medical school, and then I just figured, I thought that actually, it's not like I didn't like medicine. I come from a medical family. Like everyone in my family is a medical doctor. So it was very natural for me. And I like medicine, but it's just like I figured out that I really like math and computer science much more. And I just wasn't willing to give up that. So then I dropped medicine, moved to engineering and like came to MIT, did my master's PhD in computer science. And then, but then throughout the whole time, I'm very interdisciplinary. Like even as like when I did my PhD at MIT, for example, I was working on computer networks. So things like the internet, like how to make the internet more reliable, data faster, all of that stuff. But at the same time, I was using method from control theory. So you are from Harvard, you don't know that our department has like a double E side and a CS side. And so I was working both with the CS people and with the double E people in the department. And then as a faculty, I moved to a new domains, like, okay, I want to work with wireless signal. I like to change things. I don't, like, I'm motivated more by the problem than, okay, this is my field, I do what I'm taught to do and what other people in my field do. So I started moving to wireless signal and wireless sensing. And it helped a lot to have also a strong like mathematical background. I think when you have strong foundation in math, you can move between domains much more easily. And in fact, when I came to MIT as a student, I was in the AI lab. I was working on neural networks. At that time, actually, neural networks didn't work at all. So I decided, no, this is not working. Let me work on internet problem. Internet was big at the time, and it was like all this the dot like before the .com exploded, so everyone was like, internet is the biggest thing. So, but basically, as I said, I moved to wireless signals, but I did a bit of machine learning at the beginning when I came, and then I did I was going, as I said, to medical school. So at some point, these things like closed the circle, and it came back to machine learning, came back to connect that with health and medicine. To me, like, it's more, of course, I'm a computer scientist at the end of the day, but I'm less concerned about being in a very specific subfield of computer science. And I think it's good to try to have foundation. Of course, you're not going to be able to do every single field or move to any single field that just freely, but it's if you have a strong foundation, you can always learn the additional material to move between fields. And of course, if you have an interdisciplinary background, you can bring in new things. So the thing that I do in machine learning, being able to design deep learning networks for RF signal, is very different from someone who has no background in radio signals, for example.
And for students who are interested in learning more about ML or pursuing work in one of the fields you were just mentioning, do you have any thoughts on whether students should start on the theory side or begin with an applied project and fill the gaps, or some kind of combination of both?
So, yeah, this is an interesting question because actually, so I don't think at this stage the theory in deep learning is that useful or that connected to reality. So, but that doesn't mean that theory is not important. So, like, if you come to me, I am an applied person. I'm motivated by the problem, but I think theory is very important. Not the theory of deep learning or machine learning in particular, but it's very important to have a very good theoretical foundation, because that actually gives you a very good intuition. Like, all theory is mainly about structure and connection between the underlying structure, and being able to see through a pattern and be able to connect it together and discover the underlying laws that govern that structure. So that really gives you a lot of intuition and ability to manipulate also your data. It's not necessarily just the theory that is related to machine learning. I mean, having very good theoretical foundation or mathematical foundation I think is very important. And I think in the US, unfortunately, when we go to computer science, we neglect some important mathematical or sub-discipline in math that could be very useful to computer scientists, particularly now also as we are as machine learning scientists, you process continuous signal. You need to know something about differential equations and dynamics and all of that stuff a bit. But so to answer you, theory or practice, I think you need theory in general. You need to have a brain that can analyze theory, and these are your tools. I'm not a theoretician, so I don't use theory for developing new theory as much, although I did some work like that. It's like very interdisciplinary. So I even published some work in purely theoretical conferences in computer science. But at heart, I am motivated by the problem. I do the theory for the problem, to solve the problem. But I do think that theory is very important for thinking, like for giving you the right intuition and guided intuition.
And I'm particularly very inspired by your work specifically, and I was wondering, how do you approach evaluating projects and new ideas?
So multiple things. So one thing is that experience matters. So when you are have been a faculty at MIT, I think for more than 16, 17 years now. So with experience, your guts feeling becomes an informed guts feeling. So I follow my guts feeling. So it's like I need to really care about the problem and be passionate about it. So that part has to be there. But I mean, if you just follow purely your guts feeling, I mean, it might make you work on something that has no future, or something that is not important, or so you need that gut feeling to be informed and guided. And it gets guided by experience. It gets guided by asking for feedback from mentors and people who know about the domain. And also, when you pick a topic, it's not that when you are regardless of what the field that you work on, and particularly in computer science, when you pick a problem or a topic, it doesn't mean that you just picked it and that's it. I mean, it is there. You are going repeatedly and re-evaluating your problem and re-scoping it. So some students, they come and say, oh, I want a PhD topic, and they assume that they're going to get a PhD problem and they're going to work on that PhD problem for the next 5 years. But that it never happened that way. What happens is that you have potential problem or potential idea, and then you go and explore it a bit, and you poke into it, and you discover, okay, maybe, yeah, it's promising, let me continue, or no, actually it's not promising, let me stop, or no, most of the time it's neither these two extremes. It's let me rescope it, let me okay, if I change the definition of the problem a bit, then it becomes solvable. So I personally follow a bit of my gut's feeling, but as I said, it's informed with many years of experience in my domain. But also, I reevaluate that with the evidence that I see from the research.
And finally, do you have any advice for younger students interested in this field?
I think it's really important for students, so whether they are young or older, but particularly for young people, is to know yourself, to know what you want. Right? So not everyone wants the same thing. Right? Some people, they are very much devoted to science, and they want to build their whole life around it. Some people think about their job and they want a decent job from 9 to 5, and they want to enjoy it, but they have other things in life. And also, some people get interested with theory, and some people. So I think it's really important to know yourself and your objectives in life and in your career in particular. And if you know yourself, things get much easier, I think, because then you can, if you were asking how do you pick your problems, it tells you how you can pick your problems, it tells you how to pick your advisor, it tells you how to pick your field, what to do. So I think the first thing is try to know what you want and what fits you, not just what you want. And from the thing that you want, you have to pick the thing that fit also your character, and they shouldn't be conflicting. I want to be like rich, but I also want to work on this problem that nobody cares about. That's kind of like not gonna work together very well. So I think that's important for students to know what they want. And I think the other thing is, if you really care about science, I think don't think that you don't know something. Some students think, okay, so I am a computer scientist. I don't know anything about signals. This is like electrical engineering. Or I don't know anything about medicine. If you ask, like, anyone that we deal with here is smart enough, and if you want to learn something, you can learn it. I mean, you are young, at least like you are at the stage where you still can learn almost everything. So don't say I don't know this, I don't know X. Like, try to figure out whether you can learn X, and how much effort it will take from you, and whether it's worth it.
Thank you so much for taking time to speak with us today. It was a pleasure to meet you.
It's my pleasure. Thank you.